Miss Courtney, and we are reading in our science book on page 202, chapter 8, Watching the Weather. Weather, temperatures, and winds. The weather maker. Where does lightning come from? What causes the tornado to spin? How do clouds manufacture snow? Why do breezes blow? Why does the bright sun warm the earth less in winter than in summer? Questions such as these have puzzled men for centuries, but in recent years, meteorologists or scientists who study weather have succeeded in unraveling some of the mysteries of the sky. In this chapter, we will study some of the weather's various ingredients. In order for us to understand the workings of weather, we first need to realize that the sun is the basic cause of all weather. The seasons and winds, the clouds, the lightning, even the rain are all results of the sun's influence over the earth. A filter for solar rays. The atmosphere acts like a giant screen or filter around the earth. In order for the sun's rays to reach the earth, they must first pass through this filter. Actually, an average of only about 47% of the sun's radiation manages to get through the atmospheric barrier. The rest is either reflected back into space or absorbed by clouds, dust, carbon dioxide, or ozone. The atmosphere prevents many forms of harmful radiation from reaching the earth. Playing hot potato. Not only does the atmosphere act as a filter to block out certain forms of solar energy, but it also acts as a huge heat-absorbent blanket to keep the earth warm. After solar rays pass through the atmospheric filter, they strike the ground. The ground absorbs the solar rays and then releases the energy in rays of a slightly different form back up into the atmosphere. These heat rays are unable to escape into space, but are absorbed by the atmosphere, which in turn re-irradiates them to the earth. As if they were playing a huge game of hot potato, the ground and the atmosphere pass the energy back and forth to each other. This function of the atmosphere is preventing the Earth's heat from escaping to space is called the greenhouse effect. Without the greenhouse effect, the Earth's temperatures would plunge far below freezing every night as soon as the sun went down. Second-hand heat. The air that we live in receives most of its warmth second-hand from the ground. First, the sun heats the ground, and then the ground, like a giant heater, radiates its warmth into the air above. Because most of the Earth's heat is absorbed by air very near the ground, this air is much warmer than the air found a few miles higher up. The seasons. The Earth takes about 365 days to complete one orbit, or revolution, around the sun. As the Earth makes this journey, it also rotates on its axis, an imaginary line running through the Earth from the North Pole to the South Pole, like a spinning top. The Earth's axis does not run straight up and down in relation to the sun, but instead is tilted at a slight angle. This tilt in the Earth's axis results in the different seasons on the Earth. The equator is an imaginary line circling the Earth midway between the North and South poles. The half of the Earth's surface north of the equator is called the Northern Hemisphere. The half to the south of the equator is called the Southern Hemisphere. Because of the Earth's tilt, the Northern Hemisphere is pointed more directly at the sun for part of the year than is the Southern Hemisphere. During this phase in the Earth's orbit around the sun, the northern hemisphere has its summer, and the southern hemisphere has its winter. But a few months later, after the Earth has traveled around to the opposite side of the sun, the southern hemisphere faces the sun more directly and has its summer, while the northern hemisphere has its winter. A matter of angles. The differences between the summer and winter temperatures in each hemisphere are called by the differences between summer and winter temperatures in each hemisphere are caused by variations of the amount of solar radiation, which includes many other types of energy besides visible light, falling upon the Earth. During summer in the northern hemisphere, for example, solar energy strikes the Earth directly, producing warm temperatures. But in the winter, when the northern hemisphere is not pointed directly at the sun, solar energy strikes at a slant, spreading and thinning out over a wider area. The energy acts like a beam of a flashlight. If you point the flashlight straight ahead at a wall, you see a small, bright circle of light. But if you point the flashlight so that the beam strikes the wall at a slant, the light spreads out to make a larger, dimmer oval shape. When you walk outside on a sunny winter day, you have less solar warmth striking your body than you would on a bright day in the summertime. That is one reason your body feels colder. Another reason is that the air surrounding you is cold because it also receives less energy from the sun. In the winter, solar energy traveling at a slant must penetrate a greater distance through the Earth's atmosphere before it reaches the surface. The longer journey gives the atmosphere more of an opportunity to absorb the sun's rays or reflect them back into outer space. The increased blockage of solar rays and the shorter days giving the sun less time to warm the Earth are other reasons why the Earth's temperatures are colder in winter than in summer. The winds. Like the seasons, the Earth's winds are also created by the sun. Winds are produced by the temperature differences found on Earth. The greatest of these temperature differences exist between the equator and the poles. Tropical regions near the equator are not greatly affected by the tilt of the Earth's axis. No matter what the season, energy from the sun always strikes there directly, making the temperatures constantly warm. But the North and South poles are just the opposite. Even in the summer, solar radiation reaches them at a slant and temperatures are cool. In the winter, they receive very little solar radiation and temperatures plunge to well below zero. At any given time, the temperature differences between the tropics and the poles are very great, as much as 180 degrees Fahrenheit. Without winds, the equator would be much hotter and the poles would be much colder than they are now. God designed winds to carry excess heat away from the tropical regions and towards the poles. According to the wise plan of the Creator, this transfer of heat not only balances out the uneven distribution of the sun's warmth on the earth, but also produces the clouds and systems of weather that water the earth. But how exactly do the winds transport heat from the equator to the poles? Nothing but a lot of hot air. You have already learned that gases in the air expand when they are heated and contract when they are cooled. If air is heated, the molecules in the air spread out over a greater area, meaning that a particular area of space would not hold fewer air molecules than it did before the air was heated. Cold air is denser than warm air and holds a greater number of molecules in the same amount of space. Since warm air is made up of more empty space and fewer molecules of matter, it weighs less than cold air. Cool air is heavy and has a tendency to fall and settle near the ground. Warm air rises when heavier, cooler air gets underneath it and pushes it upward. A good example of the rising power of warm air is seen in the hot air balloon. Air inside the balloon is heated and expands greatly. It is so much lighter than the unheated air around it that it is able to rise not just itself, but the balloon and the gondola, which is the place where people ride, as well, easing the pressure. You will remember that air pressure is the weight of the atmosphere, pushing down on the earth. When warm air rises, it counteracts the downward push of the air's weight by moving in the opposite direction. Air that is moving up does not press down on the Earth's surface as hard as stationary air does. Rising air then actually reduces air pressure at ground level. In the same manner that an umbrella shields you from the rain or sun, rising warm air shields the area below it from full weight of the atmosphere. When cool air settles near the ground, it has the opposite effect on air pressure. Air pressure at ground level is increased, not decreased. The downward motion of falling air strengthens the normal downward push of the atmosphere's weight and adds to the total force pressing against the earth. When placed under high pressure, air always seeks to flow to an area of lower pressure. For example, air under high pressure in a balloon will rush out of the balloon unless the end is tight. In the atmosphere, air is in a region of high pressure behaves like air escaping from a balloon. Air always flows away from a region of high pressure to fill in a region of low pressure. And we will skip this page and go on to 208. Earth-sized winds. In the tropics, the bright sun makes the Earth's land and ocean surfaces unusually warm. The Earth in turn heats the air above it. Warm air over the tropics rises because it is pushed up by cooler, heavier air surrounding it to the north and the south. The rising warm air creates low pressure below it at ground level. Cool air from both the north and the south flows across the ground toward the equator to fill the low pressure area. On the earth, this flowing air is felt as wind. At the same time, the air near the ground flows toward the equator. Air at the upper level moves in the opposite direction. As the heated tropical air rises away from the warm earth, it cools with the increase in altitude or height until it is not light enough to move upward any further. Then it begins to flow away from the equator. As it moves away from the equator, it cools even more and falls slowly downward to the earth to replace the air moving at ground level toward the equator. The circulation is continual, with warm air rising at the equator, cooling and flowing outward, settling to the ground far to the north or the south, and flowing back to the equator to be warmed all over again. A spin makes the atmosphere dizzy. The earth is a big place. It is so big in comparison to us that we never notice its motion. In the 365 days that make up 1 year, the earth travels about 584 million miles, moving at 66,600 miles per hour. That means that if you are 10 years old, you have journeyed almost 6 billion miles in your lifetime. You probably had no idea that you were kind of a cosmic traveler. And at the same time, as it is speeding through space in its track around the sun, the Earth also turns on its axis, completing one rotation in 24 hours. Of course, you know that the Earth's rotation causes sunrise and sunset every day. But you may not have known that in order for the Earth to keep up with its schedule of 24-hour days, the Earth's surface has to spin around at over 1,000 miles per hour. To us, the Earth appears to rotate very slowly, and the sun and moon seem to creep across the sky. If the Earth did not rotate, the Earth's winds would be very predictable. Warm air would rise at the equator and flow all the way to the north and south poles, where it would cool and settle. Then, attracted by low pressure, it would flow along the ground back to the equator, warm up, and rise to begin the cycle again. To people on Earth's surface, the winds would always appear to come from the north in the northern hemisphere, and from the south in the southern hemisphere. 3 major wind systems. The Earth's rotation makes the transfer of heat from the equator to the poles much more complicated. Rising air at the equator is not able to flow due north or south to the poles. It can travel only about a third of the distance before it falls back toward the Earth and gets caught in the return flow to the equator. The flow of air is not due north or south either. The Earth's rotation bends the winds so that in the northern hemisphere, they blow from the northeast, and in the southern hemisphere, from the southeast. These winds in this part of the world are called the trade winds. The airflow away from the poles is similar to the flow from the equator. Cold, ground-level air at the poles travels only about a third of the distance to the equator before rising and returning to the poles. Bent by the Earth's rotation, the winds in this part of the world blow from the east and are called the polar easterlies. In between the trade winds and the poles, easterlies lies a region where the tropical and polar airflows meet. In these middle latitudes, the winds, affected both by the Earth's rotation and by the pressure differences between the airflows, blow out of the west. The areas in both hemispheres are referred to as the regions of prevailing westerlies. Collisions between warm tropical air and cold polar air give the middle latitudes the most changeable weather on Earth. And we will stop there for our comprehension check.